Hello, everyone. I'm Kristina Miele. I'm a structural engineer with Fastenep. I also lead the CLF New York group. So kind of, I guess, one of the mirror groups of what you guys are doing in DC. We have our own group in New York. I'm a structural engineer by training, so I work in all materials, but I have somewhat of a specialty in mass timber design and have gained some knowledge and experience with the material over the past couple of years. And our firm has a special interest in mass timber, so it's something that we've been focusing specifically on for the past 10 to 20 years. So my goal for today is to take you through a little bit about mass timber, but I can start by just kind of introducing our firm a little bit more. So like I said, we're structural engineers. We work in all materials with a special expertise in timber. I work in our New York office. Our head office is based out of Vancouver, but we also have offices in Seattle, Edmonton, Calgary, and one in Frankfurt, Germany. But yeah, so what I'd like to talk about today is kind of start, I think a lot of times in these carbon discussions, we tend to land on talking about timber as a good option. So the way I'm going to kind of walk you through this is first, okay, so we've talked about timber. How do you take that and share it with your client? Like how do you, or whether you're a client or a developer, an architect, and an engineer, what's the case for mass timber and how do you make it an appealing solution? Then from there, when does it make sense to use it? So we understand it's an appealing solution for kind of all of these reasons. Where should we introduce it into the conversation? Once you introduce it into the conversation, what do you have to consider for the design or the coordination of the building? And then last, I'm just going to touch on, okay, like you're going down this path, you're working through the design, what are some considerations from carbon? How do we look at LCAs? What are some things that our firm and we're doing to kind of make good carbon choices with timber? And then we can have a discussion from there, time permitting. But feel free to stop me at any point if you have questions. If you guys can just keep an eye on the chat, let me know if anything pops up, but also just feel free to come off of mute. And I think the idea is to kind of share ideas and kind of talk through things. So don't feel bad to stop me. So mass timber, just so we're kind of starting on this with the same vocabulary, a lot of times there's different acronyms that are getting thrown around when we're talking about mass timber, but just to kind of start on the same page, I'm mostly going to focus on CLT in my presentation for the most part, but there are also alternate options for mass timber planks, NLT, which is nail laminated timber, GLT, which is glue laminated timber, and then we're talking about mass timber systems in general. We're talking about large built-up engineered sections, something different from light frame timber construction, where we're using large, heavy sections to build buildings from a kit of parts. I just got to note that my internet is unstable, but can you guys hear me okay? Okay.
Yeah, you broke up for a quick second, but you're back.
Okay, hopefully we'll be all right. So why timber? Again, back to this idea of like, I would imagine the reason I'm here talking to this group today is because timber always comes up in conversation when we're discussing it as a sustainable or carbon smart material. So I'll get into this a little bit more later in the presentation, but just starting as a base point, timber is recognized as a sustainable material because it's a renewable resource. It grows and we cut it down. It has low embodied carbon, which means it has less manufacturing and requirements than steel or concrete. It has quick regrowth, depending on the forestry standards, but we have pretty high forestry standards here in North America, where we have more timber that is grown than is harvested each year. And that allows for a cycle of carbon sequestration. Again, I'll get into this a little bit more in detail towards the end of the presentation, but just kind of starting out, as oftentimes, especially in the carbon world, we're starting off conversations by saying, why timber? Because it's a sustainable material. So from there, there's also aesthetic benefits. I think that when you're looking into using timber, there's this idea that you can create a warm work environment or commercial environment. But now we're getting into things which I know less about, but like well standards and biophilia and just ideas for design where you can kind of bring the warmth of structure and material into the design of a building, and introduce that as a potential benefit for mass timber. Precision utilization of 3D modeling and CNC. This is really a place where mass timber shines because it is a prefabricated system and a kit of parts. So you're working with a supplier to grab sections in the same way that you would with steel or any other material. The idea with mass timber is that everything comes to site, drilled, ready to go, and kind of fits together like Legos. This is often a benefit to the client because it means that everything is coordinated ahead of time. If you have a good working relationship with the full design team, there's really a high level of coordination that's required so that everything can be prefabricated and brought to site, ready to go. And again, this kind of ties into this idea of prefabrication. So basically having everything prefabricated in a sheltered, controlled environment means that there's a lot more control on site, which allows for my next point, which is construction advantages and cost advantages. But whether it's a CLT panel or some kind of other prefabricated panel, here this is an image from an ice arena in Vancouver that we worked on, where we created custom prefabricated panels out of timber members that could kind of be dropped in place as you go. And then last but not least, construction advantages. So most people don't know much about construction of mass timber buildings because it's kind of a modern mass timber construction is a newer technology, but mass timber buildings, when compared to steel or concrete buildings, you have less deck labor. The members are lighter and easier to manipulate, so you have less people on site potentially. Here you can see a few construction workers lifting a column into place. That would be much less likely for a steel column that would weigh significantly more. Less people on site, less machinery means you have a quieter site. Schedule savings, that comes from prefabrication, which I talked about before. Lighter building means reduced foundations, and more and more we're seeing that when you take all these things into consideration, it becomes a very cost competitive option. It might be that the material becomes a little bit more expensive, but the key thing is schedule saving, material saving, and being smart about your coordination and schedules for design. So then there's this idea, okay, these are all the reasons why we're considering timber, but once we know all of these benefits, when does it make sense to introduce timber as an option when you're looking at different buildings and performance and requirements for buildings? So the current codes, typically in most places, we're pulling from IBC 2015 and IBC 2018. In these codes, timber is allowed in most types of construction, but in type 1 and 2 construction, you can have a mass timber construction at the roof only, which is still a huge benefit, especially in 1 or 2 story construction or somewhere where the roof of the building, maybe in a gymnasium, is a really big design feature. But here is an example of an elementary school in BC where it's a concrete building with a mass timber construction at the roof, which again brings some of that warmth and some of the benefits of mass timber into the building when you're in the type 1 or 2 construction realm. Then you get up into the type 3 A and B or type 4 buildings, which currently are capped off at a maximum of 6 stories in the 2015 and 2018 IBC. But the reality is, as the building stock in North America grows, there's these key, exciting design buildings, but the majority of building stock really does live within this realm of up to 6-story buildings. And where we've seen success for this is, again, in the commercial office environment, residential construction, where you do gain the benefits of having exposed timber, bringing warmth to the space, quick construction times, and kind of all of the advantages that I talked about earlier. This is the MEC corporate headquarters, which is kind of like the REI of Canada. So this is our corporate office in BC, where they used, I think it was type 4 construction, an NLT plank floor with glulam beams and columns all throughout the space. And then last but not least, there are certain cities where we're starting to see early adoption of IBC 2021, which is the next iteration of the code. And this is exciting and has really brought mass timber to the table as a competitive option in many more building types, because it allows upwards of 250 feet in a type 4A building, where you can use timber in taller construction based on how much is encapsulated or protected for fire. So when you're looking at a type 4C building, it's very similar to the type 4 heavy timber construction, where all of the timber can be exposed. When you go taller than that, up to 180 feet or 12 stories, that's a type 4B building, where some of the timber needs to be covered up for fire, but you can have some of it exposed. And then in a type A building, it's a mass timber building, but it all needs to be encapsulated or covered and protected from fire. So the benefit there is you can go tall, you can get the benefits of carbon sequestration and quick construction times, but you don't necessarily get the benefit of the exposed timber. So an example of this is a project that I've been working on. It's just topping out in construction, basically in this fall, but it's a 10-story residential building in Cleveland, Ohio, that was an early adopter of the 2021 building code, which meant that it currently is the tallest building in the US. It won't be that way for a while, but it's a 12-story building that follows this partial encapsulation requirement for a type 4B building. So what this means is that 50% of the building can be exposed with timber. And what this meant for this project was, you can kind of see in the light image on the left where you kind of see the darker hatching. That is kind of covered timber at back of house space. And then as you approach the windows and kind of more living spaces, you have exposed timber throughout the building. So like I said, that building is currently under construction. Here you see all the exposed timber coming into place, but a lot of the timber will eventually be covered with gyp throughout the center of the building, leaving timber exposed at the outsides. So key considerations. So now we have how to kind of make your case for timber, when it makes sense, what types of buildings you can use it in, and when. And then the last piece is key considerations for design to really make the design a success. So I just had a quick question here on lead time for mass timber on Market Square. We pulled our timber on that project from Binderholz, who is a European supplier, and they were looped into the conversation probably 2 years ago to bring them on board for mass timber. I don't know what the exact lead time was at the time, but usually we were looking at in the realm of like 9 months to a year. Okay, I'll finish running through this and then I'll kind of come back to the questions at the end. So key considerations, best sectors. This kind of loops into what I was talking about for where mass timber fits into requirements of the code. But again, commercial low to mid-rise buildings, we see this really popular in the tech sector. This is where you kind of fit into the current stipulations of the code up to 6 stories. And then multi-residential, when you're in that sweet spot where it's a little bit too tall for light frame construction, which is hard to compete with cost-wise, that's where in a project like Market Square, which you'll probably hear me also calling it Intro Cleveland because we've kind of shifted the name, but same project. That one is multi-residential use where the idea is that the developer is really looking for a premium on cost to have exposed mass timber in their units. And then long span roofs, or even just the roofs that I was showing where you have a feature roof. This is really popular in recreation spaces, transportation spaces, and other places with feature roofs, airports, etc. The grids are really important because we have a kit of parts and there are specific lengths and widths to the sizes of panels that can be used. You typically see a more regular grid. Here I'm kind of showing the realm of different types of grids that we look at, ranging from the smallest on the bottom left, which is a point supported system that would have no beams. I'll show an example of that a little bit later on, to the 2 systems on the right, which are a more traditional heavy timber system, and then the 45 by 20 foot span, which is where you might introduce a hybrid system where you have long span steel, precast, etc., some kind of long span beam, and then you can span mass timber panels over that. MEP integration becomes a key consideration as well. With everything having to be prefabricated and kind of CNC'd off-site, integration of MEP becomes really important. The other thing is anytime you're trying to expose as much structure as possible, you need to be clever about where you're hiding your mechanical and pipe runs. And there are different strategies for doing this. Here you can see there's 2 girders which are offset from each other, which kind of leaves a space in between beams where you can tuck in some electrical, mechanical routing. There are other strategies as well, but this becomes a key point. And then fire, which is the question that I always get asked when I tell people that I design mass timber buildings. What about fire? The key thing here is that we have learned a lot about mass timber and fire, where there are codified methods for calculating the rating of timber members, where we can understand that somewhere close to 1.5 inches of timber will burn for every hour of fire that it's exposed to. So as the engineer, we can look at a reduced section as it starts to burn and make sure that it has the capacity not to fail. The other thing that's important to understand is because we're talking about mass timber, it will kind of burn more like a log and less like light frame construction, which is more like a kindling type of fire where things can burn much more quickly and easily and spread. There's also options for introducing sprinkler systems, which are requirements in some building types. And like I talked about, some requirements for encapsulation, which really just limits the fire load depending on the size of the building. Procurement is an interesting one, and when I was talking when I was thinking about coming here, one of the questions was like, what about procurement specifically on the East Coast, or like for you guys in DC or us here in New York? The big one is Structurlam just opened a plant in Arkansas, so that's kind of exciting to see some potential supply out of the like South Central US. There's also Nordique, which is a supplier out of Quebec. SmartLam had a plant in Alabama. They may have merged with DR Johnson, but we're seeing a lot of southern yellow pine production kind of coming out of Arkansas, Alabama, this area, and then again, some production from northern Canada, but supply is becoming less of an issue as more suppliers come on board. I also included Europe here because on the intro project, for example, the supplier was Binderholz, which was out of Austria. But through the use of cargo ships, supply to the East Coast becomes a feasible option. For Market Square, for example, we had ships coming from Austria across the ocean and then through the St. Lawrence Seaway all the way to the port of Cleveland, where everything was delivered by ship. So also a good option for procurement on the East Coast. And then cost saving. So I touched on this a little bit, but this little graph, I believe it's from Woodworks, kind of puts things into perspective, where on mass timber buildings, the key thing is schedule savings as cost savings. So like I mentioned earlier, you might have a little bit of a premium on the material itself, but if you can save time in your schedule, you can save time in the cost overall. So that means there's less carrying cost, the owner can lease and occupy sooner, and this really comes from limiting foundations because you have a lighter building, erecting things quickly because it's prefabricated, using prefabricated modular facade systems that can kind of enclose the building quickly and make sure the timber is protected, earlier start in mechanical because of the prefabrication, and kind of just pushing the whole schedule forward to save time in construction. And then last but not least is carbon discussion. And I know that everyone is, or I would assume everyone's here because there's a particular interest. So I kind of just want to touch on some key points, as like I personally have started digging into some of the carbon considerations for mass timber, and also what we've been doing at a firm level. I think the best way to introduce this is to kind of dig in a little bit to what it looks like when you use timber in a life cycle assessment. So just kind of taking a step back for a second, when we're looking at a life cycle assessment of any material, we're looking at the full life of the building, from the manufacturing use of the material to the construction of it, how it gets used throughout the life of the building, and then what happens at the end of life of the building. But when we're looking at like specific EPDs, and I just chose this one from SmartLam in Alabama, one because it's a little bit closer to home in terms of a material supplier, and two because it's an approved EPD that's part of the repository of available information through One-Click LCA. So it's an approved EPD that kind of meets all of their requirements. But just to point out that when you're, a lot of times when you're looking at EPDs for materials, and you know, for this one and timber in particular, you're really only looking at that A1 through A3 phase, which is the manufacturing. So where is the material coming from? How is it extracted, transported, and manufactured, but not really looking at the rest of the life of the material because it's coming from the manufacturing constructor. So they don't know how it'd be constructed, how it would be used. And at this point, they're not responsible for what happens at the end of life of that material. So as you kind of dig into an example EPD for timber, you'll see that the A1 through A3 phase is covered. And I just thought this was an interesting point that a lot of people often ask about, you know, the use of adhesives and sealers. So they're just showing here that the product is 98% lumber and 2% adhesive and sealer. This is just, again, kind of digging into all of the elements of looking at the life cycle of a material, but the idea that the EPD itself will only cover that, you know, extraction, transportation, manufacturing stage, but then what happens after the fact is outside of the system boundary. And then you end up with, you know, a list of different impacts. So global warming, ozone depletion, acidification, eutrophication, smog formation, and fossil fuel use. That's really looking at this like A1 through A3 phase and trying to quantify the CO2 equivalent that comes from A1 through A3 phase. I also just snipped in here, the Carbon Leadership Forum has published a baseline of the 104 being the low range for CLT material, and 200 being the baseline average, 137 somewhere in the middle. But just to kind of get a sense of, here you're seeing, if you look at the global warming potential total, it's 126 kilograms of CO2 equivalent. So doing a lot better than the baseline, but not quite as low as you can get. Just to kind of give you a sense of what you're looking for when you're looking at some of this data. And then I'm going to touch on this at a high level, but it's a really important thing to kind of dig into when you're looking at timber, is really this question of biogenic carbon. So taking like 10 steps back, the reason that timber is looked at as a sustainable material is because trees absorb carbon through photosynthesis and use it to make plant tissue, which is another form of carbon, but it's living in the lumber itself. So that biogenic carbon that's stored in the tree through photosynthesis is emitted as carbon or methane when the tree dies and is left to decay. So the idea with using timber for construction is that we're utilizing that plant tissue that's storing the carbon before it's allowed to release the carbon back into the atmosphere, and using it as a storage system. So this idea of biogenic carbon is saying that in the early stages of the life cycle, you can take a lot of carbon out of the atmosphere because you're storing it as wood. But the reality is, because we're not looking at phases after A1 through A3 in the product declarations, you really have to consider what happens at the end of life of that material. Because at some point that carbon does have to come back in some way or another, and that happens either when the leftover waste is left to decay, the wood waste is combusted for energy, the leftover harvest is left to decay, it's left when you take a building apart, the wood is left to decompose in a landfill, and then kind of just what happens at the end of life. So there's this really great study by Tallwood and NetZ. It's called Cross-Laminated Timber Buildings, a Whole Building LCA Case Study, that I would recommend you take a look at. I found it really interesting. But it starts to compare, when you're looking at different breakdowns of timber, what different programs assume for the end of life of a CLT panel. So in Tally, for example, they assume that 50% of the panel is stored in a landfill and combusted for energy and actually finds its way out of the system, where 50% is left to decompose and carbon goes back into its cycle. In Athena, on the other hand, they say that only 23% decomposes and sends carbon back into the cycle. So when you start to look at the impacts this can have on how much carbon is in your LCA, you can see that in Tally, where more timber is left to decompose, let's just look at this one here, for example. When you include biogenic carbon, there's much less carbon in the equation because you're able to take it out. When you don't include biogenic carbon, obviously there's a lot more, because it's only looking at the carbon related to manufacturing. It's not saying that carbon stored in the tree can be used in your analysis. And then depending on the program and your assumptions about this, it can make a big difference in the final calculations. So definitely a nuanced thing to get into, but just something to point out to start to understand the impact of some of these nuanced things. Then there's a lot of studies out there that kind of look at the impact on all these different categories of different sized buildings. And a lot of times we're looking at global warming potential as the thing that's having the biggest net impact on global warming. And when you look at it there, you can see that mass timber building is somewhere in the 20 to 25% range of having less carbon impact than a steel building. And then as the building gets taller, you have a little bit more of an impact. Here's kind of another chart, which is just kind of showing some GWP studies of multiple different kinds of buildings, where you see a tall steel or reinforced concrete building comes in a lot higher than your 5 and 12 story mass timber building, or even your light frame timber building, just to kind of understand the range of carbon equivalents for different constructions. So we did a little study internally on just kind of looking at a single 30 by 30 bay of steel with concrete on metal deck versus glulam and CLT building. And we're finding actually close to a 50% reduction in GWP. We have a very limited foundation system. We're not looking at facades. So as you kind of add these additional components into the building, that number will continue to drop, and that's kind of where you get into the 20 to 25% range. But when you're looking at structure alone, it can have a really big impact. And the ways that we're kind of thinking about these things and trying to incorporate them into our work is to reduce the amount of timber that we're using. So if we can reduce the volume of any material on a project, there's going to be less carbon. But we developed this tool, which you can find through our website. But I just want to point it out just to kind of show, once you choose timber, that you can have a big impact on volume, which will drop your carbon numbers in general. So here I'm looking at, this is about a 20-foot by 30-foot grid. And you'll see here the total timber volume is about 0.175 cubic meter per square meter of area of the building. But if I just go ahead and drop the number of purlins, let's say I don't want to have any purlins or intermediate beams, and I just want a girder and slab system, that number goes way up because I need a thicker CLT panel. So obviously I'm going to have a lot more carbon in this building because I have a lot more material. I have a lot more beams and columns and slab. So I went up to 0.286 cubic meters. If I introduce one purlin, I can make a huge impact, drop almost by half the total timber volume in my building. And then I can kind of play around with like, what's the sweet spot? So when I add another purlin, I go up a little bit. So maybe my sweet spot is here at 0.15. But this is just to point out that we're starting at the base of saying, how can we make the building most efficient and use the least amount of material? It's kind of one thing that we're playing around with. So when we do studies for a large corporate campus like you see here, for example, we can really hone in on, okay, there's a ton of building here, but how do we make it as efficient as possible while still having the aesthetic and the benefits that I talked about earlier of mass timber, but limiting the impacts of materials in general. And the way we're doing this on an analysis level is we're assigning materials in Revit, separating groups of systems, and then pulling out that information in a tabular form to say, here's the quantity of material that we have in this building, and then kind of trying to look at those numbers and understand the impacts of the decisions that we make. In other ways, the last kind of piece that I want to touch on, which kind of links into this idea of end of life, is trying our best to make buildings simple so that materials can be reused or disassembled at some point in their life. So even if the building is not necessarily designed for disassembly or designed for reuse, a building like the 18-story Tallwood building at Brock Commons, which is a point-supported system, doesn't use any beams, has a lot of elements that kind of easily come together and are reusable in the same way that they were put together. So you have the prefabricated facade assembly that comes together as a kit of parts. I'd like to imagine that it could come apart as a kit of parts in the same way. And then on a project like Market Square, we spent a lot of time thinking about how connections come together and how the beams attach to the columns, mostly for cost savings and schedule savings. But we're trying to push this to the next level to think about how is making the building easier to put together also make it easier to pull apart. So here the beams kind of hang from the top of the columns with a special steel hanger, which clips onto a ledge on the column. Here you can kind of see an image of one of those being dropped onto place on site. But this is where we're trying to take these at end of life and send less timber to the landfill so that we can rely on more biogenic carbon when we're looking at building design. So that's a lot to have covered. I will leave it at that and maybe run through some of the questions here. But feel free to speak up if you have other questions. One was, I've heard of challenges in DC with floor plates being thicker in timber, requiring buildings to be taller or forgo a floor if they hit the max of the local height limit. That is a really good question. So timber members are typically a little bit deeper than steel or concrete because it's a little bit more of a flexible material with a little bit less strength. The key there is really like honing in on the grids and the efficiency of the system. So you have to be really clever about how all the pieces come together and kind of be smart about the depth of the system. But that's why you can't really compare like a long span timber system where it starts to get really deep. You might have to pull in the column grid a little bit to make it more efficient, if that answers that question. And then another one was, why do timber buildings have a higher ozone depleting potential compared to steel? That's also a really good question. There was discussion in actually this paper that I was referring to. Let me pull it up here. Let me from current slide. So here is where you can kind of see that the mass timber had a higher ozone depletion than the steel. And some of that has to do with the in a paper I was reading, they were talking about global issues versus local issues. The global issue being global warming potential. the local issue being issues with forestry that can lead to things like smog and ozone depletion, which need to be handled at a local forestry level. So the ozone depletion specifically, I had notes here for myself of where that came from. Eutrophication and smog are controlled by forestry regulations. Eutrophication is the like fertilizers and stuff that get used with forestry practices getting into the water and having an impact there. So that's easier to wrap your head around. The ozone depletion, I don't know actually specifically where that comes from, but the general idea is that it's part of the forestry practices, and that the quantity of it, like here you can say it's times 10 to the -2. So that means it's like 0.00003. Whereas when you're looking at other ones where it's 10 to the 3rd power or 10 to the 6th power, the equivalent impact is much, much higher than the ozone depletion. So when we did this Bay study, for example, of the timber versus steel, we saw this big spike in the difference of ozone depletion, but in the program we were running, it said not applicable. And that's because the values are so small when you're comparing them to each other that the spike isn't necessarily real specifically for that one. I don't know if that makes sense. It has to do with the unit of how you're looking at. There's very little impact on ozone depletion in general. It's a little bit higher for mass timber than steel.
Ozone depletion seems like it tends to come mostly from things like the insulation products, right? With you know, the CFCs and things like that. So maybe it's just not so much in the timber, so that's why those values are so low.
I wonder if it's coming from the glue, and like because it's the 2% of it. It'd be really, actually, that's a really good point. It'd be interesting to compare ozone depletion of an insulation material to what the ozone depletion is of timber and look at the scale of it, like you said. But maybe it is coming from the glue, and that's a really good point.
Interesting.
Yeah. The last question I have here is, am I aware of COVID having major impact on the supply chain? Yes, but to the point made in the question, a lot of industries are getting hit hard, appliances, paint, etc. Same things happening with the timber industry. Prices are going up, but I'm seeing the same thing when I'm getting prices back for steel and concrete, that like in general material supply is being challenged by COVID along with everything else.
Does anybody have any other questions?
I had a question on as if there was a way to kind of estimate what, and I know that One-Click LCA and some of the other LCA softwares do this, but is there a way to kind of estimate what the end of life or the disposal impact would be for the mass timber if it wasn't reused and if it was left to a landfill or left to decompose or something like that?
Yeah, I think that's actually the base assumption for most programs where they exclude biogenic carbon altogether, which is back to this slide basically, where in the EPD I was looking at for SmartLam, they take the -900 in A1 and then you have to put back the 900 in C3 or C4. So that's saying like it all has to come to zero basically. It's when you start to look at alternate options for end of life where you can start to bring back some of the negatives, like, and allow yourself. So the more conservative way to look at it is to just exclude biogenic carbon altogether and just look at the manufacturing impacts of timber as a material. The reason I want to challenge this as an idea is because the whole benefit of using timber is to store the carbon. So I feel like rather than just say, okay, what is the manufacturing of timber and what's the impact of manufacturing of timber versus steel, we like need to rethink how we're thinking about that and say, like, how do we actually make timber a useful material by making use of the biogenic carbon? So to just say ignore it because it's conservative feels like a cop-out of finding an actual solution.
Yeah.
But that's the better way to not make wild claims that won't come to life, you know?
Yeah.
So.
Looks like we got another question in the chat.
Okay.
Are there any emerging methodologies which include carbon storage in forest soils?
Oh, hi, Eli. I don't know the answer to that. I'm sure that there are. You probably know more about that than I do.
Well, no, I'm sort of hoping there are originally, because we certainly study a lot of that, you know, on the forestry side, and we see forests building soils. So to me, the whole conversation about storage and buildings is really important, but it's not the whole calculation. And
Yeah.
I think it's fine as long as we maybe acknowledge that it may be doing more and don't try and rush to quantify it. I still just think we shouldn't, we should, hopefully some methodologies are going towards maybe addressing that in different forestry regions that practice soil building forestry.
Yeah. Yeah, it's a good point. And then like almost within the like very structured realm of how an LCA is carried out, you miss out on all these other impacts, which is kind of maybe your point.
Awesome presentation though. Thank you.
Thanks.
It looks like there's another one that popped in the chat as well.
Yeah. Does biogenic carbon capture depend on more on specific details like tree species? Yes, totally. That is why there's been a lot of discussion. Like I was involved in a moderated discussion between the design industry and the forestry industry to kind of try to address, to Eli's point, things like carbon storage in forest soils or species and forestry practices. It's things that, as is in the design industry, we don't have PhDs in forestry, so we don't know all the nuances of forestry practices, but how are we at least asking the right questions so that we understand impacts on biogenic carbon is kind of the point. So yes, all of those little details matter a lot, and that's kind of how you start to look at where those numbers come from and how they can vary so much depending on which study you're looking into, right? And what the assumptions of the study are, and that's kind of the idea. And then someone was asking about distinction between CLT, DLT, GLT, et cetera. Just the G, the N, the C basically have to do with how the members are attached, whether they're nailed or glued. But the big distinction between cross-laminated timber versus the others is that these are one-way spanning systems. They utilize the strong axis of the member to span in one direction. CLT actually turns the member on the flat and crosses the direction in different laminations, and that gives it some two-way spanning capacity, which means you can do things like we did on Brock Commons, where you can eliminate the beams and use it more like a concrete slab where it's spanning from column to column in two directions. You couldn't do that with a DLT or a GLT product.
Great. Did that answer all the questions? Well, this was really helpful. I appreciate you taking us through all of your research and your tools, and appreciate your time. If anybody has any other questions, feel free to reach out. Have a good day.
Great, Kristina. Thank you.
Thank you, guys.
So much.
Bye-bye.
Thank you.